today's problem from linear programming problem, and the problem is solve the LPP by big M method. Okay, and the problem is maximize Z. This is equal to 2x1 minus x2 plus 5x3 subject to three constants are given. The first constant is less equal to type, second is equal to type, and third one is the greater equal to type. Okay, now to use big M method, that is the simplex method, we must have to transfer this LPP into standard form. Okay, and to transfer it to standard form, here we use a slack variable. The name of this slack variable is let x4. Here we use a surplus variable because this is greater equal to type. Let the surplus variable is x5. Okay, and now we must have to get the standard basis of the form 1 0 0 0 1 0 and 0 0 1 in the starting table. Okay, and we get 1 0 0 by using slack variable in the first constant, but we cannot get these two starting vector. Okay, so we use two artificial variable, namely this is x6 and x7. Here in the second constant we use x6 and in the last constant we use x7, and the standard form of the LPP becomes standard form is given by max z. This is equal to 2x1 minus x2 plus 5x3 plus 0x4 plus 0x5. This is slack, and this is surplus. Okay, and now we add the artificial variable x6 and x7 with the coefficient minus m into x6 and minus m into x7, where m is the large positive number. Okay, and the constants are subject to, we write x1 plus 2x2 plus 2x3 plus x4 because this is slack plus 0x5 plus 0x6 plus 0x7, this is equal to 2, and the second constant is 5x1 plus 6x2 plus 8x3 plus 0x4 plus 0x5, and x6 is the artificial variable, that is x6 plus 0x7, this is equal to 24, and for the third constant, one surplus and one artificial, this is 4x1 plus 3x2 plus 2x3 plus 0x4 plus, sorry, this is not plus, this is minus x5 because this is surplus, this is subtracted from this relation, plus 0x6 plus x7, this is artificial, this is equal to also 24 with xj greater equal to 0. For j, this is equal to 1 to 7. This is the standard form of this LPP. Now we draw the first simplex table, and we first put the coefficient matrix here. Okay, here since 6 variables, sorry, there be 7 variables, so we write here 7 vector a1 to a7, and we write all the column vector one by one. The first column is 1 5 4. Okay, 1 5 4. Second is 2 6 and 3. the third one is 2, 8, 2, and the next one is 1, 0, 0. This is 0, 0, minus 1, and this is given by 0, 1, 0, and this is 0, 0, 1. Okay, clearly these three column A4, A6 and A7, this is A4, this is A6 and this is A7 are forms the standard basis. Okay, so we write here the basis vector. These are A4, the first basis vector 1, 0, 0, then we write A6 and then A7. Okay, this is A6 and this is A7, and write the corresponding variable. This is X4, X6 and X7, and now we put the value of B which are given by the right side column. B, sorry, this is 2, 24, 24. This is 2, 24 and 24. Now here we write the Cj, that is the cost vector. These are given by the coefficient of objective function 2, minus 1, 5. We write here 2, minus 1, 5. These are 0, 0, minus m, minus m. Okay, we already said m is the largest positive number here. Okay, that is minus m is the smallest negative number, and we put Cb, that is the cost corresponding to the basis vector, which are given by A4, that is 0, which are given by A6, that is minus m, and A7, that is minus m also, and this is Zj minus Cj, and these are the net evaluation or cell evaluation of each column. Okay, we find net evaluation of each column one by one. How to find net evaluation? We multiply Cb with this column, that is this and this vector are multiplied by dot multiplication, and we get the result as 0 into 1 means 0, minus m into 5, this means minus 5m, and 4 into minus m, this is minus 4m. So minus 9m minus Cj, Cj minus Cj means this minus 2. So we get minus 9m minus 2. This is the first net evaluation, and this is given by 6 and minus 3, that is minus 9m, this is plus 1, and this is given by 8 and 2, this is minus 10m minus 5, and this is 0, this is given by m, this is given by 0, and this is given by 0, and we find out the greatest or smallest number or greatest negative number. It is clear that minus 10m minus 5, this is the smallest negative number. Okay, and since m is the largest positive number, so minus 10m is smallest. So this indicates that this is the incoming vector. Okay, so A3 is the incoming vector here. A3 is incoming. Okay, now we find out the mean ratio. How to find the mean ratio? Mean ratio is given by the column B is divided by the column of incoming vector, that is 2 divided by 2, 2 divided by 2, this is 1, 24 divided by 8, 24 divided by 8, this is 3, and 24 divided by 2, 24 divided by 2, this is 12, and clearly this is the minimum of the ratio, and in this reason this column is named as mean ratio. Okay, so we get this is the key column, entire column is the key column, and this is the key row where minimum of mean ratio occurs. Okay, and now the vector in the key row, this is clearly A4. This indicates that A4 is outgoing from the basis. So this is outgoing vector. Okay. Now we have to find the key element. What is the key element? Key element is the element in the intersection of key row and key column. Clearly this is key row and this is key column. So obviously these are the intersection of row and column, and this is key element. Okay, we write here key element. This is key element. Now we go to the next table and we make the key element is 1 and other two element of this column is 0 and 0, and then this A3 column becomes as A4 columns 1 0 0, and automatically by the operation of matrix A4 in the form of another vector and A3 in the form of 1 0 0. Now we draw the second simplex table as we fill first the basis vector column. Here we already says that A4 is outcoming vector and A3 is incoming vector. Okay, A4 is outcoming. Here also we write A4 outcoming. Right. Now we write A3 in place of A4. Here we write A3 and next two vector A6 and A7 remains in the same position, A6 and A7. Now here we write X3, X6 and X7 corresponding variable. Okay, and clearly CB is given by A3 corresponding to CB is 5, A6 corresponding CB is -m, and this is also -m as usual, as previous. Now here we make the operation. The operation of the first row is given by R1 dash. R1 dash, this is equal to half into R1, because we have to make this key element to 1. So we must divide all the row by 2 and getting the result as from this column we get this is 1 because 2 by 2, this is half, this is also 1, this is 1, this is the key element, this is half, this is 0, this is 0 and this is 0. Okay, and since this element is 8, so to make this is 0, we here write or make the operation R2 dash. This is equal to R2 minus 8 R1 dash. R1 dash means new R1. Okay, so we have to multiply new R1 with 8 and then subtract from the old R2. Okay, and similarly for R3 dash we get this is 2, so we make the operation R3 minus 2 into R1 dash. Okay, and then this becomes 0, so we write first this column 0 and 0, and by similar operation we write all the elements like this. This is 24 minus 8 into 1, this is given by 60. Okay, and this is 5 minus 8 into half, this is 1. 5 minus 4, this is 1. This is 6 minus 8 into 1, this is given by minus 8 into 1 means 8, this is minus 2, and we complete by the same argument the table. We get another 2 row as the given operation. Okay, now we calculate the net evaluation one by one. By the similar argument, we first calculate this net evaluation. What is the net evaluation corresponding to A1? This is minus m into 3, minus m into 1, 5 into half. Sum of these 3 minus 2. And clearly this is given by minus 4m plus half. Okay. And similarly we calculate all the net evaluation of the matrix. Now it is clear that minus 4m plus half, this is the most negative net evaluation. So clearly this indicate, that is the most negative net evaluation indicate this is the incoming vector. Okay, and now we calculate the mean ratio as this is 1 by half. This is 1 by half. So this is 2. This is 16 by 1. This is 16 by 1. So 16, and this is 22 by 3. 22 by 3, and clearly this is the mean of mean ratio. Right? This is the mean of mean ratio. So this row is the key row and this is the key column, and so in the position of intersection of key row and key column, this is the key element. Okay, and clearly in the key row there be the vector A3, and it is shows that A3 is outgoing vector. Okay, and this is outgoing vector. Here we write A1 incoming and A3 outgoing. Now we draw the next simplex table. This is the third simplex table, and since here A3 is outgoing vector and A1 is the incoming vector, so we replace A1 by A3. Sorry, A3 by A1. We write here A1. These are same, A6, A7. Okay, corresponding variable are X1, X6, X7, and the cost coefficient corresponding to A1, this means 2, and these are minus m, right? And since this is key element, so here the operations are operation, and this is the mean ratio. Okay, operation are given by R1 dash. This is 2 into R1, because we have to make it 1. So we get the first row as this is 2, this is 1, this is 2, this is 2, this is 1, this is 0, 0, 0. Okay, and clearly this is 1. So we make the operation R2 dash. This is equal to R2 minus R1 dash. This is the new R1 or new first row, and this is 2. Okay, so we get this is 15. Sorry, this is not 15. This is 16 minus 2. This is 14. This is 1 minus 1. Obviously 0. This is minus 2 minus 2. This is minus 4, and similarly we get all the element of this row, and we write here the operation R3 dash. This is given by, this is 3, so we operate here R3 minus 3 R1 dash. Okay, and by same argument we complete the element of this table. Now by the same argument we completing the table, and also we find out all the net evaluation. The net evaluations are respectively 0, 9m plus 5, 8m minus 1, 9m plus 2, and this is m 0, 0. So it is clear that all the net evaluation Zj minus Cj get equal to 0, and this is nothing but this is the condition of optimality. Okay, so optimal condition reach, but it is seen that still at that position the artificial variable or artificial vector, that is A6 and A7, still in the basis. Okay, because A6 is here 0, 1, 0, and A7 also 0, 0, 1, that is in the basis, and the value of the variable or artificial variable is positive. This is 14, also this is 16. Okay, so we say that the LPP or the given LPP has no feasible solution. Here we write two important lines at the end of the solution to understand this argument. And we write here, since all Zj minus Cj greater or equal to 0, so the condition of optimality satisfied. But two artificial vector, here we write A6 and A7. Here A6 and A7, two artificial vector, still in the basis with positive label. This is very important term, positive label. Why positive label? Here x6, that is the variable corresponding to the artificial vector A6 and variable corresponding to the artificial vector A7. x6 this is equal to 14 and x7 this is equal to 16, which are greater than 0, also greater than 0. Hence we say that hence the LPP has no feasible solution. Okay, this is the complete solution of the problem, and this type of problem is very important problem for your exam. Thank you for watching.